Okay, so Jeff,
All right,
take it over.
thank you. I'm gonna kill my video. I'm gonna kill my video because save bits. I unfortunately my connection isn't perfect. So I'm still here. So how do I hide the silver? I guess this is okay. Anyway, so thank you all for taking time out of what I'm certain is an extremely busy week, especially for the senior members of the lab who are obligated at S. So what I'm going to talk about is different than what anybody's ever seen before. It's related. So if you've seen me talk in the last couple of years, I've talked about parallel research kernels, but this is going to be different. And I'm kind of excited to talk about it because normally it doesn't align with what I'm doing in my day job to talk about it. So even though I was doing this for a couple of years in my free time, I didn't really have any venues. And since you all are curious researchers and probably have interests well beyond Intel product, I figured I would take the opportunity to exploit your open-mindedness and talk about this. This talk was mostly yesterday. And it is very unpolished. So for you all and the audience listening at home, this is designed to be, the data I'll show at the end is extremely raw, and I will redo it again if I ever take it anywhere else. But I I used some data from my desktop while I was, running a web browser and GUI. So as I will note later, it violates all of Torsten's rules, and so it is not reproducible scientific computer science, but it's interesting. And the good news is, I do subscribe to Lorena's theories on putting all your code on GitHub and making it reproducible. So in that respect, any of the data you don't like, you can absolutely obtain yourself. Any experiment you would like to do. So that's one fun parts of this. Which button?
Jeff, we're honored
Okay, so
that you would show us.
I will thank a number of people. So this project is a long-running project. Actually found references from the 1990s to Tim Mattson.
Jeff, can you hear us? Looks like we lost him.
Yeah.
Yes.
Yeah. Mini? No.
Mini not here. Yeah. Probably lost him.
Oh, yeah, he's still on.
Okay.
Okay. Maybe he'll come off. Yeah, maybe he'll go out and come in. Yeah, he went out.
I see. Yeah. All right.
Our recording has stopped. Okay. Oh no, you're
Okay. Thank you. So I think, anyways, you could read the slides for posterity. So I have a number of people to thank, and actually, of course, I'll thank Lissandro for his very prompt and kind peer review on some of the code that was written, and I also have to thank Ejon, or aka Tim, who I'll refer to him by his legal name because of the multiple Tims, but he's an undergrad at Georgia Tech, and he actually contributed some really good code, and I'm really excited about this. And so this is also, I think, an opportunity to talk about the fact that undergrads can make some really amazing research contributions, even if you don't even know them. In Tim's case, he actually emailed me out of the blue a different project that I had worked on with Argonne, and he said he needed something to do for the summer, and I said, well, hey, you could contribute to the Parallel Research Kernels, and he did, and it was amazing. And so I'm really happy that Tim is the second greatest contributor to the PRK project this year, and I hope that he has time to contribute in the future. And I will also thank Brad Chamberlain, who didn't contribute any code, but Brad really inspired the study that I'm going to talk about today, for reasons that I'll explain later. And I will acknowledge the people's contributions, some of them when other people contributed directly to the data or to the code that led to the data with smiley faces. So I'm going to briefly go through the PRK project, tell you what it is, why we created it, and I'll give a little more historical context than I have given in the past because I sort of wanted to put it down somewhere. So the PRKs exist for programming model evaluation, which of course is not, we're not the only ones that want to do that. And there are some standard methods. I would say the most popular one going back a while is the NASA parallel benchmarks, which are actually one of the major inspirations for the PRK project. If you look at what we've done, what we've created, it's actually pretty similar to NAS and HPC Challenge. It's just if you look at the size of the code, we have created something which is, you could think of it as the second or third distillation or, you know, refinement on or coarsening, I suppose, in a multi-grid sense, on those proxies. So those proxies were exist relative to real applications, and we created a proxy for the proxies because we needed to be able to develop code faster. And that's really what you'll see here is that, in contrast to a mini application, which is an important activity but a very difficult one, you know, Lulesh might be a couple thousand lines of code. The essential part of a PRK is anywhere between 3 and 12 lines of code, and that's fundamentally different. We learn different things. Clearly, we learn less about some properties like complexity and software and whatnot, but we learn more in the sense that you can do a lot more studies and you can do a lot more ports. And as you'll see here, other than the programming model or programming language benchmarking game, which isn't really HPC oriented, and the Rosetta Stone website, I don't know of anything with extensive language coverage as we have or getting towards. And so there's some value in doing this, having the breadth. And I absolutely believe in depth as well. And I do a lot of work with mini apps in my day job, but we wanted something that we could go quick and learn new things without much work. And as you'll see, it turns out that even the amazingly simple, you know, triad-like vector addition kernel reveals a non-trivial amount about programming languages. And so this is actually much of the data I'll show. So obviously there's, you know, when you do these measurements, you're looking at different things, and the PRKs are designed to really focus on one or two properties at a time, very, very simple. So either a synchronization pattern or communication pattern that you would see in a more complex algorithm. But really by focusing on a very specific feature, you can make sure that that's what you're seeing, because that's the only thing you're seeing. If in most cases, the PRKs lack significant computation, and it's somewhat intentional. And also it allows you to think about the design space more exhaustively. An example I've talked about before, we won't talk about here, is in the case of the wavefront synchronization kernel, the way that gets implemented in different architectures is very, very different. And I originally didn't understand it and therefore didn't like it, and eventually came to just think it's the coolest part of the PRK project. And we have learned a ton about software and architecture from it. And it's literally the simplest piece of code you can imagine for a loop carry dependency. So our goals, one, we want to be universal. We're not. Obviously, we think of ourselves as being reasonably covering the set of algorithms that are represented in the NAS parallel benchmarks and HPC challenge and some related things, but everything is static and everything is HPC derived, or you know, may connect to other things, but it's definitely HPC focused. And of course, we don't have anything for machine learning. We don't have much for dynamic algorithms, although Rob has done some recent work on adding AMR and PIC proxies. which are sadly really, really complicated because, as I think most of you know better than I do, things like adaptive mesh refinement are not simple, and you cannot distill them down to one line of code or two. But Rob is still nonetheless worked to create some even simpler versions and maybe some of the proxy apps. Portability is really, really important. It's been important to me as long as I've been programming because I work on NWChem, which is supposed to run everywhere. From a Mac to a supercomputer, and the PRK project does. I know that because I have a Raspberry Pi next to my desk, and I have a Xavier AGX ARM NVIDIA card next to my desk, and I have a NUC, and I have a Mac, and I ran these on Blue Gene before it got turned off. And so they're very, very portable. If they're not, it's my fault, and I want you to submit a pull request, no matter how esoteric the platform is. If I can port to it, I will. Extensibility. This one's important because if you look at the parallel language benchmarking game or whatever studies that are out there, they're fixed problem sizes, and in many cases, they're toys. Our implementations are parameterized such that you can run them on a Raspberry Pi and you can run them on 100,000 cores of a Blue Gene or a Cray. And we've done that. We published a paper where we scaled them all the way out. And so there are knobs there to do that. And in that respect, because they're parameterized to be extensible, they're not in fact benchmarks. Benchmarks have a fixed input such that you can, or some structured in nature of the input like LinPack. And we don't do that. We say, okay, you can do what you want with it. If you want to fix the problem size and use it for some purpose, fine, you can, but we're making them extensible. And verifiability, we are not perfect. I have occasionally misunderstood IEEE floating point exceptions and verified correctly that I had NANs. Hopefully that's fixed now. But in general, you cannot get the wrong answer and get a performance number. It will first verify that you've computed the answer correctly, and then it will tell you what the performance was. That's intentional because some of the programming models we use occasionally have bugs in them, and some of the programs that people write have bugs in them, and we don't want to deceive people and give them a number without making them earn it with correctness. So the PRK suite has a bunch of different stuff in it. I focus on the 4 kernels in bold, which have pictorial representations. This talk is only going to focus on 2 of them, basically because I was gathering data yesterday and I only had so much time. And because, of course, I haven't written all the code for all these, as you'll see later. These are actually really, really important, even though they're simple. So the first one in the lower right that matters is obviously this. It's like stream triad. It's not exactly, and I'll elaborate in just a second. It's a vector addition. This is a good measure of memory bandwidth. It's also a really good way to measure runtime overhead. If you are measuring vector addition, there is no synchronization, whether it's parallel or not, and other than the barrier to say you're done. And clearly, any difference you see between the low-level C implementation and anything else represents the overhead of whatever language. That's important because we want to measure those things. And in fact, that's what we do in this study later. The next one that's interesting to me is transpose. Matrix transpose is kind of what you get if you do a 3D FFT, or if you do a tensor contraction, or if you in the limit of a bucket sort where your statistical distribution is homogeneous in some respect, you can end up with something like this. So it's good at generating an all-to-all pattern on the network, or of destroying your TLB or whatever. We use a 2-dimensional star-shaped stencil as another kernel. 2D stencil, obviously not very interesting from a physicist perspective. But as I think I've been told by experts, that in some limits of, if you're doing 3D stencil codes, you eventually get down to something that's pretty thin in one dimension as you decompose, if that's how you do it. And so 2D isn't entirely wrong. It's also the intersection of solving PDEs and doing convolutions and image transforms. which of course I think people now understand as being really, really important from an AI perspective, but people have been doing Gaussian blur in Photoshop for quite some time, and that's really just a stencil kernel. And so because Intel sells computers to more than just physicists, it is important for us to have some representation in a kernel. Lastly, the one that I have spent a lot of time on in the recent past is this, we call it sync P2P or wavefront, but it's basically this loop carry dependency update. And this is similar to what you get when you do, I think it's the NASA LU benchmark, the trailing update or something. It's if you don't block it, I guess. It's also a lot like the deterministic neutron transport codes that people at Livermore and Los Alamos care about. And it also has a strong similarity to the sequence alignment pair HMM algorithm. And that's because it's just similar to dynamic programming, which of course gets used for string alignment. So you'll see it in genomics and stuff. So it's a really interesting kernel, and I should probably write a paper about that someday. But anyways, we've done a lot with that one. So some interesting commentary or things that you might not see if you just glanced at it. So we have a very careful license caveat to emphasize that we are not providing a McAlpin stream. We're providing a near derivative of it that is unofficial. So you cannot call these stream numbers. You can call them PRK N stream numbers, where N is for not. But one of the things that we did, I think Rob did it for verification purposes, is he accumulates the output vector instead of overwriting it. And that, of course, means you can make sure you don't skip an iteration or something like that. But what is also interesting about it, and this has actually come up rather recently, is if you've ever run stream on an x86 processor, you may be familiar with the impact of non-temporal or streaming stores, which are a store that doesn't allocate in cache. It doesn't do a request for ownership on write, and which is not the traditional x86 store. And so you can see often significant differences in bandwidth depending on whether or not your compiler generates that instruction. It will be theoretically 1.33, et cetera, X difference, for basically 4 memory operations versus 3. And this is really, really important if you're going to, use GCC on an AMD processor and ICC on a Xeon, because ICC generates that instruction and GCC doesn't. And this is why AMD, when they run stream, use a different compiler. But this is obviously not something you want to surprise people with. And so I have found that the fact that we have the accumulation in there guarantees that we do the update rather than the overwrite. And it means that the PRKN stream numbers are more stable. And maybe that's good, maybe that's not good. There may be value in saying overwriting is a good measurement to take. But in our case, it has made it easier to have people get the numbers they want. Stencil, obviously, as I said, is 2D, and that has some good and bad reasons. The transpose, we insist that people do it with a 1D decomposition because we want to see the all-to-all pattern. This is really important on the network. The difference between an MPI all-to-all and a bunch of small messages and a send-receive of communication pairs between nodes is very, very different, and we don't want people to cheat. I understand there's algorithmic reasons why, with pencils and slabs and those things, but we wanted to be consistent. And I will admit that I have actually cheated because I think I used Petsy, and I let Petsy decompose a 2D matrix, and Petsy probably did something that wasn't what I wanted, but the Petsy ones are still work in progress. Lastly, sync P2P is, as I said, is quite interesting, and it's different if you're in distributed memory. It's an interesting synchronization benchmark, and if you're in from a point-to-point stance, if you're in shared memory, it turns out that you have a whole bunch of different choices, including using fine-grained data flow. If you're on a GPU and you can't do that, then you have to use barriers. We have a very interesting implementation using cooperative groups that has been useful, and it's a great way to understand some GPU models, but I'm not talking about that today. Okay, So now I'm going to talk about the history. I haven't talked about this before, but I think it's important to describe the phases and how we got to some of these things, because I noticed that a lot of academic projects sort of change their name every time they get new funding, and there's not a lot of persistence in some of these research projects. Maybe people graduate, whatever. But this is a long running project, and it has sort of been reborn a couple of different times in different ways, and yet remains sort of coherent, which I think has been kind of fun. So as I said earlier, Rob and Tim basically created it before I joined Intel. When it was created, and it remained for many, many years, a C89 MPI OpenMP project, and that would be MPI 1, and that would be OpenMP 2.5. So it was not focused on programming models, it was focused on architectural features. And Tim had done some chip CPU architecture projects in the past where he'd wanted to understand things, and so in that sense, it was being used more from a hardware perspective for a long time. They weren't doing anything with programming models that was interesting. They were just focused on the algorithms and the implications to hardware. And I joined Intel in about 2014, and we decided that we were going to use the parallel research kernels to answer some problems about exascale, because there was a debate in that era about whether or not MPI was going to stick around to exascale. Could MPI get there? Things like that. And then there were a bunch of, sort of, PGAS was known and established. New dynamic runtime system type models that we were being told might be relevant. We should give up our MPI and use something new. And we wanted to do a scientific study. So we run, and this is a big team group effort, as you'll see in I think a slide or two. We decided to write a whole bunch of new stuff. And in some cases, those weren't C89 models. Charm++ and Grappa are C++, not C89. And even if C89 is a subset, that they're not the same language by any stretch. And then UP is, formerly C99. And so we said, okay, we're going to write these things, but we stuck with a C89 base. We didn't really move away from that. We just sort of added the minimal amount of new language to each of them. And at some point, and I can't even remember now, Brad Chamberlain and the Cray team decided to do some Chapel ports. And it became obvious during this time that we needed to grow out of C89. Because at the very least, as we were told correctly by the Charm++ group, you can't write Charm++ like a C programmer. That just doesn't work. You obviously can't write Chapel like a C programmer. And even if you could, it's not a good comparison. Chapel does not exist as a competitor to C89 and MPI send receive. I don't think anyone thinks that anymore. There was a time where it wasn't clear enough to people that they weren't competing with each other. It wasn't MPI versus Chapel in any direct sense. Chapel deserved to be compared against things like Fortran co-arrays or Python, for example. And so we thought, okay, well, if we're going to go there, if Chapel's going to go there, maybe I should go there. And so it was really Brad's work, or the Chapel team. I don't think Brad wrote all the code. I think somebody else did. But it was really the Chapel work that inspired a lot of what you'll see here. And in particular, Chapel makes some very interesting trade-offs between semantic expressiveness and elegance and performance. And they have two versions in their implementations, which aren't in our repo because I just have never gotten around to doing the merge correctly. But they have pretty code. And what that means is it's the most elegant, expressive version of Chapel they can write. And then they have a different version, which is like the fast version. And it doesn't necessarily mean pretty is slow. It just means one of them is tuned for performance and the other is tuned for readability or expressiveness. And this is a really important distinction to consider when you're designing software and your application software or programming models. And so you'll see now, I actually created some versions that are intentionally using the pretty style as opposed to the fast style, and sometimes the performance is noticeably different, and sometimes it's better in the case of some of the scripting language, and some cases it's worse. So this is a useful thing to evaluate. I eventually did a bunch of stuff with C++ and Fortran, and I probably need to go faster. And I would say the next phase of the project is multi-GPUs. I'm not talking about that here, but that's the next phase of understanding. So this is the work from ISC 16. This is when I got involved, and I want to say I think this is a pretty good paper. Now it's maybe not as interesting because people believe that MPI will make a text at scale, and I don't know how many skeptics there were in 2014, but there were some, and hopefully they've given up. So this is just the stuff. You can read all the details in the paper. So we were able to show differences here. And in particular, MPI does pretty well, but more importantly, MPI, it's not just MPI per core, it's MPI plus shared memory that prevails, and the details I think are in the paper. This is transpose. What you see here, this crossover point, this is a hybrid programming model and this is not. And the reason that changes is because on a Cray machine, as your message size drops below 1 kilobyte, your packet overheads go up, and obviously that means that the performance changes. So even though SHMEM is extremely efficient, when you push it into the 8-byte message regime, the efficiency goes down. Whereas when you do MPI with shared memory, you aggregate messages at the node level. So that's the difference. And of course, if you did SHMEM plus OpenMP, you would see the exact same effect. It's not MPI, it's just we chose to write MPI plus hybrid. Okay. So at the end of that study, and totally coincidentally, I changed jobs. I moved from Intel Labs to the Algaris group at the time, and there was an element of what was next, and so I said, okay, well, time to learn some new stuff. So I will say, from a progression standpoint, I had been doing MPI for about 10 years, and I said, well, maybe I should learn some new tricks. So I get some new skills. Maybe I should learn C++. And so I decided in 2017 to bet on two things. One of which was I had been raised at Argonne to believe that C++ was snake oil, and so I was deciding maybe that I needed to change my views on that. So I was going to learn modern C++, and I was going to learn Cocos and Raja, because these DOE folks kept saying they were important, and I was like, okay, well, I guess somebody has to understand this, at Intel at least. And then the other thing I decided was that the only growth in parallelism in HPC was for the next few years was going to be heterogeneous node level parallelism, and I was going to ignore MPI for a while, which I did. I didn't completely ignore MPI, but I mostly stepped back. And it's funny because in 2017, towards the end, I stumbled on something called SYCL, which I've been told people are familiar with now. And obviously SYCL is a big part of my life and my day job now. But when I stumbled on it, it actually wasn't part of an Intel product plan. And so it was actually a very, very funny coincidence that what I had decided to spend my free time on at work dovetailed into something pretty significant for me at work. That's just funny. So this is the summary of, and I will say, sadly, I haven't written a paper about any of this stuff because I don't really have time to write scientific papers anymore. But what we've done here is we have tried to capture a number of different parallel models and language models and cover the two-dimensional space. We don't do that perfectly. We kind of let MPI stay where it is because I was ignoring MPI for a while, but we did, co-raise is the PGAS for Fortran to complement UPC. I've written OpenMP in every language, in part because OpenMP doesn't always behave the exact same way in different languages based on your compilers. The Fortran and C syntax is occasionally different, etc. So there's some new stuff here with Python and MPI, and I think somebody wrote Chapel plus MPI, but I haven't looked at the code. So anyways, this is where things are. The C++ extras don't even fit in the box. There's a lot of stuff there, but I'm not talking about C++. So if you want to know about the C++, I gave a couple talks on this. I'll actually say it's funny because the first time I ever gave a public talk about sickle was at KAUST 2 years ago. And when I did that, it was funny for me because I was definitely not allowed to talk about what Intel was doing with sickle, but I talked about sickle because I had honestly stumbled on it in my research life. And I knew that it was going to be a big part of the future, but I couldn't tell any of you that at the time, obviously. But you were in fact witness to the first ever Intel talk that I am aware of that mentioned sickle in the context of the PRK stuff. So now for I guess this is the end where this is the new data. So the hypothesis now is, well, we've evaluated distributed memory, we've evaluated C++ and sickle and OpenMP and Fortran and all those things. Well, why not do the same thing for other programming languages, in particular, maybe the not so HPC ones? So that's what I've started doing for a while now. And it's, I'd love some help because I don't have time to do all the work correctly, but I have gotten a little bit of help, and that's moved us forward. So this is where things are now. So Tim or Ejon wrote the Java stuff from C89 conversion. I've written Julia. I have attempted to write Go, Lua, and Nim, none of which I claim to understand in any useful way. I barely understand Rust. I understand a little bit of Python. Thankfully, Lissandro understands a lot of Python and was able to correct some of my most grievous errors when I showed him the code. And then also there's Octave and MATLAB. And the reason these are here is because I figured if Brad was going to put in the effort to get somebody to write Chapel code, then it was worth comparing Chapel to things that Chapel deserved to be compared to, like Julia and Python and whatever else. And honestly, the other part of this is sometimes I just get bored and decide that I'm going to learn Go today. And so I write a PRK in Go while I'm in a meeting. So you'll see here the check marks imply sort of how far along we are, whether we've got something elegant. And in the case of 3 check marks, what it means is we've got the traditional loop-based Python, we've got a NumPy version, including a Numba version. I don't know, I haven't done anything with Numba yet, but I've put in the directive. And then MPI for Pi, which some of the MPI for Pi codes are good, and the stencil one needs a lot of work. It's very, very slow for reasons I don't understand. But please, when you see all of this, understand that it would be rather ridiculous if I was qualified to write in all of these languages. And so clearly the quality of this code does not match the quality of C that I write. And so, I hope that I've done a decent job, but it could be that I have missed some expressive features that would make the performance better. But I still think what you see is mildly interesting. So this is the initial language showdown. I'm intentionally not including all the details. I have an Ubuntu 20 Hades Canyon Nook. I use the built-in toolchain with the exception of Julia because there was a bug. So I use Julia 151 straight off their website. I use GCC 9 straight out of Ubuntu. Everything else, including Go and Java, came out of the package manager, as did Rust. The Python in this case is the one API Python distribution only because that's the one that works, because I'm dumb and don't know how to get Python configured properly unless Intel does it for me, and so fine, I did. The interesting thing about that is Intel's Python distribution of NumPy is built with OpenMP enabled, and I didn't know that. And so I ran some things with OpenMP enabled, and the performance was bad. And then I turned OpenMP off, and the performance is better. And that's because I guess the problem sizes. But so let's look at the data. So the left side is a vector addition that is close. It's not. I don't think it fits fully within it, but it was basically a smaller problem size of 1 million elements, so that I could run things like Lua and Octave, which are dog slow. You see here that when you use colon notation in Octave, you get a 2500x speed up. So obviously do that. That's a simple lesson, but please never ever write loops in Octave if you don't have to. Lua not designed to be fast, and I don't plan to. If you're going to add vectors, you should use NumPy, and when you use NumPy, it goes 100 times faster, and that's obviously why you should use NumPy all the time. This is one thing that Alessandro told me. I wrote MPI for Pi with traditional Python, and he basically said, don't do that. If you're going to use NumPy or MPI for Pi, you should always use NumPy, because why are you using MPI if you care so little about performance? So I deleted the non-NumPy MPI for Pi in response to that. At least I think I did. Anyways, so what's interesting about this is that Go and Rust, which I thought were, supposed to take over the world for C, from C, don't work as well as I expected them to. I don't know why. I haven't looked at assembly. I need to do some work to understand this, but I was surprised by that. Maybe they're just generating bad code and it's my fault. The other one that was surprising is how good Java is. And I checked the code and I can't see anything wrong. I'm getting bogus data. And so I am left to assume that I have been making fun of Java for a very long time for no good reason. It is better to tell Java is amazing. And unless I can invalidate these results somehow, I will have a lot of respect for Java for a long time. And that's kind of amazing. Okay. Now transpose. Transpose is slightly more interesting. This includes some differences in implementation, and for that I apologize, but I don't always have the ability to write exactly the same code in every language, because not every language has the exact same features. So when possible, the loops are blocked. In some cases, you can't make the intrinsic block. Well, it could, but you don't know that. And I know in the case of the compiler guts that they don't for some of these Fortran things. But what we see here is, once again, Java is somehow amazing. Fortran loops are amazing, as you'd expect. Something is going on with C. C should do better than that. And I was gathering this data at about 11:55 p.m. last night, so I apologize for not having all the answers. One thing you can see in the C++ cases is that if you use range-based for or for each, you lose some things. Some of that is because of how you can block the loops. It's also, there's some impact from the compiler and when you use a template versus a normal construct. But Julia comes out pretty well here, as does NumPy. NumPy is obviously using an intrinsic for matrix transpose. And Rust now catches up and is roughly on par with C. But it probably could be better. Lastly, because I knew my audience, I wanted to talk about MPI for Pi, and this is just to say that, for the basic stuff like stream triad or triad-like kernels, you notice the overheads, and I don't know what the overheads are precisely, other than that they're totally consistent with the sequential version. So this is not an MPI for Pi problem by any means. But for transpose, and I will say Lissandro helped with the peer review of this code more than anything else. And that's, I think, why these are good. You see now for something non-trivial, MPI for Pi competes very nicely with MPI 1 and C89. And I will tell you that one of those codes is a heck of a lot easier to read, write, and edit than the others. The Python version is incredibly compact and very easy to understand. It looks basically like, pseudocode you'd find in a paper. And the MPI version looks exactly what you'd expect from C89. So it is not really expressive or fun to read. And that's, yeah. Anyways, so that's the data. Again, I have no idea how Java is this good, but more to him. Julia does really come out quite well. I will say in my case, I had help from the Intel Julia team. Kieran was an Intel Labs colleague and understood. He's one of the folks that got a 1 petaflop in Julia on Nurse Cray. And so that he knows what he's doing, and you can see there's code changes that are a result of Kieran telling me that I was writing Julia stupidly. So you have to get the JIT compiler to turn on and all those things. And you have to change your code a little bit to do that. NumPy did okay, not as good as Julia. And I will say, when you're not in NumPy, Julia beats Python very, very significantly. So if you can, if you're not writing NumPy and intrinsics all day long, you should really switch to Julia. I'm surprised that Rust and Go aren't better, but again, those languages exist not because of performance, but because of safety and some other things. I'm not really going to say anything about C, C++, and Fortran because choose between C++ and Fortran based upon the performance of vector addition. And then lastly, I will note that I had more trouble learning MPI for Pi than I expected, but only because I know way too much MPI, which is to say that it took a while to train my brain that the capitalization made a difference and that I could skip some of the arguments and some things like that. So that wasn't any, that was mostly that if you have read the MPI standard cover to cover multiple times, you probably need to read more documentation than if you just looked at MPI for Pi from a novice perspective. And now I'm towards the end. So I will say this, you know, I'm biased, obviously I'm the producer and the consumer, but we've gotten a lot of the PRKs internally and a little bit externally that some folks have seen. Please, again, this data is totally preliminary and should be thrown away, and I'll start over next time, but I wanted to get something out there. And sometimes desktop performance is interesting because people do science on their desktop. But it definitely doesn't meet any of the torsion rules. Lastly, and I think that, you know, house people probably versus university, but you know, there's often a tendency to consult the experts and stop there, and certainly I did that, and the PRK project has consulted many experts over the years and gotten a lot of peer review, which has been really valuable. But the other thing that's really nice about it is the PRK project is actually accessible to someone who is an undergraduate looking for something to do over the summer, as you, John, was, and he was able to make significant contributions in a relatively short period of time. And so this is a project that is accessible to a full spectrum of people, and I've been pleasantly surprised at how much we've been able to get out of people who are relatively inexperienced with HPC as a whole, but who have a specific skill, as Tim did, or sorry, you, John, who he knows he's as an undergraduate computer scientist, he's pretty good at Java programming, and so he was able to make a pretty big contribution with his Java skills. And I think it took about a week, so it was really quite good. So, anyways, that's the end. These are just the papers if you want to read more about it, and I hope this is somewhat useful.
Great, thank you so much, Jeff. You know, I understand those are preliminary results, but you're telling us to switch to Java, basically, right? At this point in time.
Languages that start with J. No, I don't know that anybody should switch to Java. I mean, I suspect in some limit C++ will beat it out, and maybe I'm just doing something wrong, or the compiler, whatever. But I would say that we should not make fun of Java. I don't know, maybe I was the only one who made fun of Java, but I certainly did, because I thought that HPC, and I was wrong.
Interesting. Yeah, great. Do we have any question from the audience for Jeff? All right. Jeff, you call it PRK.
Mm-hmm.
Why not RPK? It's maybe a pretty question here, but why you call it PRK, not RPK?
What does RPK stand for?
Oh, research parallel kernel. Why research is in the middle here?
Oh, this is a funny story. Okay, so I told you Tim created it, and Tim named it the parallel primitives because it's a bunch of primitives. Okay. Now Tim's worked for Intel for decades, right? So Tim wanted to open source the project, and you can imagine that when he went to the approval process with the name the Parallel Primitives Project from Intel Labs, the branding lawyers obviously got a little bit perturbed by that, because there's an Intel product known as the Intel Parallel Primitives. Yeah. So I don't know where Tim went from there, other than it was expedient from a research or from a legal perspective to include the word research, and to make sure that it had no overlap with any existing brands, trademarks, et cetera, et cetera. So it became the Intel Parallel Research Kernels as a result of the open sourcing process. And you can ask Tim Mattson the next time you see him why he chose PRK and not RPK. But I'm just happy that it's all on GitHub.
Yeah, it's good. You also looked at one of the kernel, the dense matrix multiplication. You have not covered it here. What did you find out as far as dense?
Well, lesson one, call BLAS, don't use loops, but you know that. So that the reason I don't do much with that kernel is because you can use it to say who can optimize triple loops better than somebody else, and I don't do those studies because the point is no one should do that. They should call a library. Now you can use, I have done that. And if you actually look, the place where I've used it recently is in GPU stuff. So it turns out that the performance of DGEM as a function of matrix size and versus not. And so I did do some stuff at some point with, I actually turned it into a batched matrix multiply driver and used it to study kernel offload overhead in NVIDIA. And that code's in the repo. More recently, but I'm using it to try to understand multi-GPU stuff, because obviously the communication pattern of a DGEM is, there's more opportunity to. I haven't done much with it lately, but yeah, that's what it gets used for. I mean, his story was, I think Tim put it in there because you have the N stream kernel to measure bandwidth, you have the DGEM kernel to measure peak flops, you have you have these different things which measure different properties of a system like latency, bandwidth, and whatnot. So that's why it was there historically. But I prefer, as I think to always let the experts give me my linear algebra libraries. I don't write them myself. So in that respect, I just haven't done much with it. The one that I actually want to do more with so there's this branch kernel in the very, very beginning. And the way Tim designed it, it's actually designed to torture branch predictors, which you can imagine is interesting to an Intel microarchitect or collaborator. So the code is very specific to C. So I've been thinking about a branch 2.0 kernel, which is designed to torture the SIMD type properties. So as everybody, right, GPUs don't like divergent code. It's bad, don't do it. And vector architectures, AVX512 has mask instructions, ARM-SV2 has some stuff. And to me, we need a better way to understand the differences between those architectural implementations, and we need a good way to measure hardware. Obviously, CUDA doesn't change necessarily, but the underlying microarchitecture implementation of CUDA does. And so I've been thinking about how to design a kernel that allows us to understand the differences and similarities between a CPU and a GPU. And that's hard because obviously you have to come up with something that isn't biased, which satisfies all the other properties of extensibility, reproducibility, et cetera, is tricky. So I don't have an answer yet, but it is one of my goals to add stuff in that direction, because I don't really see anything out there in the community that lets me understand those questions already. Whereas I do see, of course, there are plenty of things that can teach me about DGEM.
Yeah. I have a question, Jeff, sorry. The Java results that you showed, what implementation did you use to get them? OpenJDK or the native or official Oracle JDK?
Hold on.
Do you remember?
OpenJDK 11.0.9 from 2020.
Okay, great.
Yeah, I genuinely didn't even expect Java to do that well, and so once I realized it, I kind of didn't know what to do with it. Although apparently VTune supports Java, so I think I'm gonna throw VTune at it and see what happens.
Okay.
Jeff, one workload sort of that I think maybe missing in your current suite, workload that would do mixed precision, right? Some sort of mixed precision in one of the kernel. It could be, for instance, a simple dense matrix vector multiplication that is, a critical actually operation for computational astronomy. And we could do mixed precision for some of the blocks within that matrix, and then do the operation accordingly. So I was just thinking whether you would also look into how programming model may impact such workload, or the other way around, how such workload can impact the programming.
Yeah. Well, okay. So the first, at this point, Tim has a very busy day job that doesn't include the PRKs. I'm basically the only person working on it at the moment.
Yeah.
Although Tim is sort of, you think of, he's the chairman of the board and he has veto power. Although he's never used it. I would be very interested in that, but I will need help. So the things, if you look at the criteria, up with something that meets the first 5, then we can do it. I would say start with is just take the kernel and just make it mixed precision, which I think I started doing because you need SGEM on some of the cheap GPUs. And I could do that trivially. I can turn DGEM into SGEM into HGEM into BF16 GEM, etc. I can also mix the precision of the matrices.
Yeah.
Again, that's not necessarily as complicated as what you want, but that's the start. But I would need help, in particular, like the scale-free graphs or whatever, like Graph 500 has an input, right, that to come up with a matrix that actually we can't have a fixed size. And then the other part of it, we need to have a way to verify it that isn't as expensive as computing it. It's computing the problem itself. And so if there are such matrices, like weird matrices, like toplets matrices or whatever that you can do things fast, things like that. If you can come up with something, then let me know and we could do it. But that's my next phase after I do the multi-GPU stuff. I think is going to be the divergence thing.
Okay. Branching. Okay. Okay. Great. All right. Any question from the audience? Hello? Did I hear your voice, or maybe not?
Just thanks.
Yeah. All right. Yeah.
Yeah. Thank you all. And I think everybody knows where to find me, and everything's on GitHub. So find me on Twitter, Gmail, GitHub, Intel, whatever. And if you want to talk more about it, it's completely open. I've never turned down a pull request that I understood. And we have all sorts of external contributors. So please, if you're bored and you want to write something new, that'd be awesome.
Great. Thank you so much, Jet. Thanks for your time. Appreciate it.
Thank you.
Thanks, everybody.
Thank you.
Bye.
Bye-bye.
Bye.